Okay, so thank you very much, everybody, for attending this new seminar from IAU Commission J1 on the spectral energy distribution of galaxies. Today we have a really nice seminar from Professor Zhanwen Han. So Professor Zhanwen Han received his PhD from the University of Cambridge in 1995, and he served as director of Yunnan Observatories Chinese Academy of Sciences from 2009 to 2014. In 2022, he became president of the Chinese Astronomical Society, and since 2018, he is associate editor of astronomy and astrophysics. So his research interests focus on the evolution and observational study of binary star systems, as well as related astrophysical phenomena, including type 1a supernovae, hot subdwarfs, double degenerates, binary population synthesis, evolutionary population synthesis, and the far ultraviolet excess in early type galaxies. So it is really, we're looking forward to this seminar. He will give this talk on the very interesting topic of the role of binary stars in spectral energy distribution. So thanks so much, Professor Han. Zhanwen, please take it away so you can share now.
Okay.
Thank you.
Let me share screen. Can you see my screen?
Yeah. Uh-huh.
Yeah.
Okay. Yeah, fantastic. Good.
Yeah. First, I would like to thank Ignacio for your kind of invitation and for your introduction. Hello, everyone. I would like to talk about something about the impact of binaries on the spectral energy distribution. My talk is outlined as follows. First, I will give an introduction. Then I will briefly overview the single star evolution. Then talk about the major types of interactions of binary stars. In this talk, I mainly focus on the effects of binary interactions on the population synthesis. And at the last, I will briefly introduce the Yunnan model, that's our model that's with binaries, and summarize. Just for IU J1 Commission is mainly about the spectral energy distribution of galaxies. You see, for a galaxy, normally for a distant galaxy, we are not able to resolve the individual stars. What we can see is that the integrated spectral energy distribution. So we need to know the properties of the stars, their masses, their age, and things like that. So evolutionary population synthesis is the approach to derive the physical parameter of stellar population of galaxies from SED observed. Actually, evolutionary population synthesis has a very long history. The pioneer is Beatrice Inslee. Actually, in her PhD thesis, she proposed the EPS. During the 90s, EPS had experienced a very rapid progress. We see that the starburst gas field and Marsden model packages pop star quite a lot. I mean, the most popular model may be the BC03. I mean, that's lots of citations. For us, we have built our Yunnan model. But in our Yunnan model, we have binaries included. We have something hot subdwarf used as a red dwarf. Also, for the EPS model, BPAS, that's the very popular one. That's developed by JJ and their collaborators. Their model, they have calibrated the observables from binary population synthesis. the ingredients of EPS model include the following. First, we need to know the star formation rate, that is, how many stars we have. And also we need to know the initial mass function, that is, how much mass of each star has. And also we need a stellar evolution model, how those stars evolve. And also we need a spectral library. That's the for each star, what their spectral like. So all those things that integrate, we got the sum of all the spectra of the star, the integrated SED. And here is the basic logic for the EPS model. So this is the figure taken from John's paper. So this is an HR diagram. This is a S-crop. So that's from 0.001 giga-year, 0.01 giga, 0.1 giga to 1 giga, and I think that 10 giga-year. Yeah, so we can see that as the age increases, the population becomes colder, so the temperature becomes low. Also, this figure here that taken from Gross paper. So we can see the SED evolves with age. We can see as the population gets older, there's a significant drop at the short wavelength. So that means if we get the spectra, we can derive the age of the stellar population. It looks quite simple, but things are not that simple. We have binaries. Binaries has a system with two stars. The two stars are gravitationally bound to each other, and they orbit around a common center of mass. The first binary star was discovered by William Herschel in 1781. With his telescope, he showed that two stars orbiting each other. That means Newton's gravitation law can be used to systems out of our solar system. So that's quite important. So the binaries were discovered. Now we know that many stars are in. So this is a figure taken from.
So sorry to interrupt, Zhanwen. So to all members, could you please mute your microphone? Could you all please mute your microphones? Thank you.
半个月了吧，已经。
I'm not. Can we do something? Do something to mute them altogether.
Yeah, I'm going to mute them as many as I can. So
yeah.
So please go ahead. Sorry about that.
Yeah.
Yeah, please go ahead.
Yeah, it's okay. Yeah, actually, this figure that taken from a review by Chainter that published by in Progress of Particle and Nuclear Physics. So here, actually, this is the update of figure of Dash and the Cross. This paper that's the annual review paper. They updated mainly for the massive stars. So the axes are that the mass of the primary star. The ordinate that the correction of band slot in percentage. So we can see that when a star is more massive, the binary fraction is much higher. For our sun, that the binary fraction is about 50%. If for a star, something more than 10 solar mass or more, almost all of them are in binaries. Binaries there are a lot of binary interactions. Binary interaction produce something very exotic. They produce something very important. For example, binary evolution may produce type 1 supernovae. We know that with type 1 supernovae, we measure the distance, the cosmic distance. We know that the acceleration of the universe is the expanding of the universe is accelerating. So we infer the existence of dark energy. Also, binary evolution produce double black holes, double neutron stars, and that's the sources for gravitational wave, and also the merger of double neutron stars produce heavy elements. And the binary evolution also leads to the formation of redefined pulsars, binaries, argos, blue stragglers, bipolar pairs, nebulae, hot substance, and then lots of things that's important. So now we know that around half of stars are in binary system, and the binary evolution alters the fate of the stars. And the key question for this talk that how do binaries modify the spectral energy distribution? And now I would like to talk a little bit about the single star evolution. For a single star, it's always assumed that the star is in hydrostatic equilibrium. That means there is a balance between gravity and pressure. Here we can write the equations for stellar structure. The first equation is for the mass. The mass equals the density times by the volume. Then the second equation that's about the momentum. So that's the Newton's law. So normally a cell here, that it will be the net force that should be zero, and then how energy is transported by convection, radiation, or conduction, and also how energy is produced. Normally, energy is produced by nuclear reaction, the change of thermal state, and also neutrino energy loss, something like that. Then the last equation is about the chemical. Because for nuclear reaction, they can convert hydrogen to helium, something like that. At least stellar evolution has been studied for quite a long time, and there are many codes to start stellar evolution. Nowadays, the popular code are STAR, that's from Cambridge, PARSEC, that's the Padua code, and the Geneva code, Yale code, and the MESA. MESA now it seems MESA cannot dominate the community. So most of the young people, they use MESA code. Here I show a movie that shows the evolution of one solar mass star. This is taken from Bill Paxton web page. So this is the HR diagram, the surface temperature, surface luminosity. We can see how it evolves. That's the central density, central temperature, and that's the profiles of the structure of the star, how it changes within time. So now we can do this quite automatically. Here is the HR diagram of single star evolution. That's data mass 0.5, 1, 3, 5, and solar mass. So we can see that the more massive a star is, the more luminous and the temperature is higher. So, and also, given the mass of star, we can determine its evolution track. For one solar mass star, it's from main sequence to red giant, then it comes to white dwarf. Here, there's a diagram for the life of a star. So for a star, not so massive, it's the life in the main sequence, red giant, and nebulae, and the white dwarf. If the star is more massive, the N8 solar masses, it's maybe main sequence, red giant, then supernova explosion, it produce neutron star or black hole. This is a figure taken from Hager. The axis are the initial mass of the star. The y-axis, that's about the metallicity. You can see that for if the mass of the star is less than 9 solar mass, so the destiny, the fate that a white dwarf. If the mass is a little bit larger, then it will end at a neutron star, that's supernova explosion. Then later, that's black hole, that's direct collapse black hole, that's black hole by fallback. So this is with supernova explosion. This is not. And later here, if the mass is even larger, between 140 to 260 solar masses, we can see that that's the formation of pair instability supernova, PISN. That means that for stellar evolution, so normally it's from main sequence, equal to giant, and to remnant. To the remnant could be a white dwarf, neutron star, or black hole. So given the mass, the fate of things that can be very well predicted. Now I'll talk something about binary interaction. Actually, there are lots of types of binary interaction, but here I mainly only talk the major interactions. In the study of binary stars, there is a very basic concept, the Roche. This is a binary star. That's star 1, star 2. They orbit around the center of mass. So that's a tetra particle. So there are 3 forces on the tetra particle. One is the gravitation from star 1, gravitation from star 2, and the centrifugal force. So by this, we can write the potential in this system. From this potential, we can see that that's the equipotential surfaces. So for each color, for the line of each color is coming to one potential. So we have 5 special points, area 1, like region 1.1, like region 2, 3, 4, 5. And these 5 locations, the net force here is 0, so there's no force here. So if we enlarge the central part, we will see there is a critical surface that equipotentially passing through area 1. This is what we call the Roche. So that means when star 1 fills its Roche, the mass will be transferred to the center. So we can see this is the better star. Star 1 is more massive, so it evolves faster, and it pans. When it pans, it fills the Roche. The mass is transferred from the primary to the secondary. And for the mass transfer, what we call it as stable Roche overflow. For stable Roche overflow, that is the mass transferred from the primary to the secondary at such a rate that is low enough so that the secondary can accretate. So it can accommodate the mass accreted. In this case, after the mass transfer, all the envelope has been transferred to the secondary. The core of the primary is left. So in this case, we have a wide binary system. The core of the primary can become a white dwarf. If it's a helium core, if it keeps burning, it can later become a neutron star or a black hole. But the mass transfer is not always so stable. Sometimes the mass transfer rate is very high. The mass transfer rate is so high that the second star could not accommodate the mass accreted. In this case, envelope will form. That's the common envelope. The common envelope engulfs the core of the primary and the secondary. And the embedded binary, they don't rotate with the synchronously with the envelope. So there is a friction between the embedded binary and the envelope. Due to the friction, large amount of the orbital energy is deposited to the envelope, and the envelope could be ejected. If the envelope is ejected, so we will get a binary system with a very tight orbit. But sometimes the envelope is so tightly bound, the orbital energy is not enough. It must not be ejected. In this case, we will get a merger. The merger normally would be more massive and faster rotating. Here, that's a plot, a figure that we call a binary linear tree. So for this figure, there are two parts. This is for low mass binary, this is for high mass binary system. So you see they are quite complicated. But this is actually is not all. In real case, there are many more channels. So from this binary evolution, we can get something very interesting, some double black hole, double neutron stars. These are LIGO resources, and also double white dwarfs. These are sources for LISA, and also type I supernovae, all kinds of things. But the basic problems, though for this figure it looks very complicated, but the basic problems, really we have two problems. One is the mass transfer stability. So during the mass transfer, whether the mass transfer is stable or not. If it's stable, the result will be the evolution will result in formation of a wide bandwidth. If the matter is not stable, then a common envelope will form. For a common envelope, envelope can be ejected from a tight bandwidth or not ejected to form a merger. So these two problems are actually in binary community. That's long-standing problems. So actually we have developed a model for the mass transfer stability over the last 20 years. So here, that's the rational. So the rational radius, and that's the radius of primary star. So whether the mass transfer is stable or not, the mainly determined by R1 and RL. So during mass transfer, RL changed and R1 also changes. And if compared to the rational radius, the stellar radius expands faster. In this case, the mass transfer is unstable. Mathematically, we can define some exponents. That's how the radius changes with the mass transfer. So we define three exponents: theta AD, that's the adiabatic change, that is thermal change, that's the change of rational radius. So in these three cases, if theta L larger than theta AD, then the mass transfer is dynamic time scale. See here we say the mass transfer is unstable. Or here the thermal time scale. In this case, that's nuclear time scale. Nuclear time scale is what we call stable mass transfer. Actually, over the last 20 years, we have established two models. So here I just only introduce the first one, the dynamical time scale methodology. This is for the basic equation of stellar structure. This is for the adiabatic methodology model. So in this model, we assume the mass is lost adiabatically, but they keep in hydrostatic equilibrium. So we keep the entropy unchanged. So this is the criterion we have obtained. The third line, that's what we said for main sequence star, for giant branch star, RGB star, and AGB star. In the binary population synthesis, normally they use a constant, but actually, sorry, Ignacio, I only have 45 minutes. Is that right?
Yeah. So yeah.
Oh, in that case, I should speed up.
Yeah, that's fine. So we have about, normally the talk should be, so you have like an extra 30 minutes, but we can push it a bit more and then we will have some time for questions. So.
Oh, okay. Yeah, in that case, I should
Thank you.
speed up. Yeah. So in our model, we can see that normally for retrogens, for polytropical model, the matter transfer is always unstable, but in our case, it's not. So we can see, I mean, the red line that's polytropic, the third line that's from our model. So that's we can see it's quite different, but we can see that our new model fits observation very well. This is from polytropic model. The third line that's from our new model. Also, that's for matter transfer. Not for the common envelope. For common envelope, this is a figure taken from Natasha Ivanova. The common envelope, there are two stars here. There is paired in the common envelope. So during this pairing, the orbit shrinks and the envelope expands. And common envelope, that's the concept was proposed by Pashinski in 1976. Since then, lots of simulations had been made, but it's very time consuming. But in binary population synthesis, we use a very simple prescription. Normally, that's about energy prescription. So we need to compare the band energy, how much band energy we have, and how much energy we can be used to overcome the band energy. One is the orbital energy, the other is the internal energy. So there's a parameter here. So that's normally used in binary population synthesis. This one is widely used. So we just talk about the matter transfer common event of evolution, but we have no time to talk about the binary device now blue stragglers. So now I need to talk about something about population synthesis, the effect on population synthesis. For population of single stars, we know the population cools down with age, but the boundaries make things very different. In this context, I list the several cases that the boundary interaction will change the population. They change the SED. One case that during binary evolution, binary interaction, donor core exposed and ignited. So therefore, stable radial flow, the core exposed. So the core normally is much hotter, and it's ignited. So when ignited, so it becomes hotter. The other way that from communal ejection, after the envelope is ejected, and the core is exposed, and also after it's ignited, it also becomes very hotter. So that means those kind of binary interaction make the remnant something much hotter. So the examples are the stress stars. They are with very high temperature or hot subdwarf stars. The second case that for mass gainer, zero stellar binary evolution, the very star with lots of mass. So that means this star is more massive, and a lot of fuels get into the star. The star evolved just like a more massive star, so that's rejuvenated. Examples are blue stragglers that in globular clusters. So they can be 2 times that of the turn-off stars. The third case that's a merger. During common evolution, if we don't have enough energy to eject the envelope, and the two stars collides, the merger is more massive. In this case, is rejuvenated. That's much hotter. Examples are blue stragglers can be from merger of two stars and out the hot subdwarfs. But for these two, they are a little bit different. For this, is simply that it's more massive. But for hot subdwarf stars, that two helium stars that's dead. I mean, they are cold, two cold helium dwarfs. They are not burning anything. They merge to become a helium burning star. The star ignited. So that's something different. But that's from the merger. Another case that's the accelerating process. So during stable Roche flow or common event of ejection, we have something a core. I mean, they could, if it's a degenerate core that becomes a white dwarf. If not, it's a helium core. It's keep burning. It can become a neutron star or a black hole. So if it's become a neutron star, a white dwarf, a black hole may actually emerge from the secondary star. So in this case, they produce X-ray, UV. So that's something. Examples are X-ray binaries. The X-ray could be black hole or neutron star or cataclysmic variables. The X-ray is a white dwarf. And the last, actually, it could not be the last, but that's the last case in my list. During binary evolution, we can see that the evolution tracks like this. If there is no binary interaction, the evolution a star will evolve to a giant. So that means, I mean, if it's a single star, it could be more luminous. But if it's a binary star, the mass transfer is from A, B, C. I mean, that's the starting point of the mass transfer, the end point of mass transfer. So the star will go hotter and cool down. So that means binary interaction makes the luminosity lower. So that means that for a stellar population, the mass luminosity ratio would be higher. So here I show if we include hot subgroup stars in your population, that's something I did many years ago. So this SED at different ages, on the 1 giga, 0.5, 1, 10 giga a year. So the black part, that's only for a single star. But if we include the formation of hot subdwarfs from binary evolution, we can see it contributes to the part that is right, the short wavelength here. So that we use this to explain the UV aperture of elliptical galaxies. So I present a paper by Hernandez Perez Bruzo. Actually, he did this compared to BC not 3, the BC not 3, and the single star model, this binary model. It actually in their binary model, they only include this channel, the merger of double helium white dwarfs. So we can see there is a UV aperture here. And also batteries can be used to explain the soft atome emission from elliptical galaxies. So this is a Chandra image of NGC 3379. After those points were taken, and this is soft atome emission, that's the unresolved. And this is from the K-band. You see they are quite similar. Why is that? Actually, the X-ray emission are from activating white dwarfs. In the spectrum of an activating white dwarf is something like this. There's the green line here. The dashed line that's from black body spectrum. So we can see that it can produce soft X-ray. This work was done by Chen and Lev Youngerson and their collaborators. You can see that the soft X-ray, they can use their model of weather algorithm to explain the soft X-ray of elliptical galaxies. Also, binary stars can be used to explain the reionization of the universe. And we all know that for the reionization of the early universe, the biggest problem that we don't have as many ionizing photons. But the binary evolution can produce ionizing photons. Here, that's a figure taken from Goldberg. So for a binary star, it was here, and the mass transfer stripped the envelope of the birth star, and the core evolved like this. You see, it becomes something very hot. And a simple calculation shows the ionization photon here at 1.8 times that of from single stars. And also there is a time delay for this, for the emission of the ionizing photons. I couldn't remember the exact number, something 10 or 100 million years. That means those ionizing photons can be efficiently used to for reionization. And also for hot X-rays for starburst galaxies. That's mainly from high mass batteries. There's two figures taken from Van Bever and Van Bever vision. So that's a different types of batteries. This shows they use this high.
他们家就不上时代无限平方码的，对对。
These high energy batteries to explain the hard energy of starburst galaxies. So lastly, I will introduce a little bit our Yunnan model. Actually, we did our average linear frequencies more than 20 years ago. Then we started to include the binaries. To show the concept, we show here, first we assume all the stars are in binaries. The black dots the black dots, that's for the primary. The red circles, that's for the secondary. So in this case, the red panel indicates we don't allow for any binary interaction. In the left panel, we have binary interaction. We can see the HR diagram that's quite different. But because for clarity, we only showed a small number of binaries. So it's something like that. But here we have more binaries plotted. Here that's the SED of that population. The black line that are with binary interaction, the red line is without binary interaction. We can see through the difference at the short wavelengths. So binary interaction contributes more to the short wavelength. These are for the colors. We can see the black dots that's with binary interaction. So we can see the colors are bluer. So that means to derive physical parameters properly from a given SED, we need binaries. So in our Yunnan model, we use the stellar average tract from Cambridge code. And then we adopt the Basel spectral library, and then we take into account the binary interactions. So we can include Blues checklers, hot subdual star, everything value, rejuvenated star, something like that. For our Yunnan model, if we here, that means we use the same set of assumption. One is with binary interaction, one is without. If we have the binary interactions, so we can find for the population, the stellar mass would be smaller. It would be fainter, and also it would be bluer, and the mass ratio would be bigger, and the UV plug will be larger, and we have some UV and average emission. And if we use our Yunnan model to derive the physical parameters of a population, we find that the population age is larger by about 20%. The methodicity is larger, and the photometric redshift would be much more accurate than that without binary interaction for blue faint galaxies. And also, we found that the binary population could have some effect on netting photons, and also it can contribute to the far infrared band, and also the star formation rate will be different. So for the next slide, we mainly focus on star formation rate in the netting sources, because for those are things that are more interesting to the galaxy people. So here we show that the binary interactions are important for SEDs of all star population at short wavelengths. Now for the next for this slide, we'll talk about the star formation rate. Because for galaxy people, star formation are something very important. The star formation rate indicator could be from X-ray, UV, recombination, emission length, far infrared radio. I mean, something like this. The X-ray that's mainly from X-ray binary. The UV that's mainly from the massive stars themselves. That's the direct. The recombination line, emission line, the far infrared, that's also mainly from the a measurement of the ionization photons in the radio that's from the supernova shock. Actually, all those indicators are affected by binaries. Here, that's a figure taken from John Chair. She shows the star formation rate, a relation between star formation rate and the H alpha line luminosity. We can see that with binary interaction, if we consider binary interaction, the star formation rate derived will be decreased by 0.2 in depth. So that's systematic. Also, Zhang showed in her paper that the intermediate age star population could be another source for H2 regions. Here she showed two figures at the BPT diagram. So that's for age the red line, right, that's with binary interaction, and the black not. So for an age of 30 million years, you can see it's quite different. So without binary interaction, it's here, but with binary interaction, it's here. And also we can see the boundary between star forming galaxy and the AGN moves to upper right. So that would be relevant for galaxy studies. So sorry, I take too much time in the summary now for this slide. The binary interactions reshape SED significantly, and the binary effect might not be neglected for the study of old stellar population using short-wavelength observations. Thank you very much for your attention. Thank you.
Thank you very much, Zhanwen. So I'll just change the color here. So thanks so much. That was a really, really interesting talk, and you see how important binaries are in stellar evolution studies. So we have now some time for questions. So what I would do, given the number of people, maybe it would be better if you could please raise your hand and then unmute yourself. Well, I'll let you know, but please raise your hand. I mean, in the meantime, I would like to ask you, so you said, I mean, there is this figure always that you have about 50% of stars being binaries, and especially when you go from massive ones, it can be even all the way up to 100. But now the question is, do people have an estimate of what is a fraction of those binaries that will end up at common envelope?
For common envelope, normally it's something for all the binaries, normally about 20% of those stuff will come to common envelope. Because for the common envelope evolution, normally it's from the red giant binary. So that means the object period must be located in the red range. So that range for red giant is something that's about 20%.
20%, which is basically because I would imagine, I mean, those that are white binaries that in principle, even the Roche lobe is large enough, in principle, there won't be any evolution different from what you would expect in a single population, right?
Yeah. Actually, not for massive stars. I mean, most of the massive stars, their evolution will be affected by binary interaction. But for low mass stars, the case is different. So for low mass stars, because the interaction is not so often.
Okay, thank you. We have a question from Paul Beck. Could you please switch on your video and mute yourself? Thank you.
Professor Hahn, thank you for a very interesting talk. I also have a question on the current envelope phase, because you mentioned the binding energy and you said it's a simplified version. Do we understand the binding energy well, and what are the factors going in to decide if we have current envelope ejection or a merger? What's the current status?
Actually, that's a very good question. Actually, to be honest, we don't understand that much. Normally, we use the prescription that is quite simple. So the band energy that is mainly the gravitational binding energy. So the uncertainty is that you have no idea how much mass will be removed, how deep the envelope is. So during the removing or ejection of the envelope, there are some changes for the core. This also that means the energy, the band energy also changed. So actually, that's quite complicated. But we did something last year or this year. We have a modified version for the model. So we calculate the band energy of the envelope. That's the I mean, it's quite hard. It's quite difficult for me to explain. So we just during the envelope loss process, we take off the envelope and then we calculate the band energy. And then by taking every shell of the envelope, calculate the total band energy. So in this case, we can measure precisely the band energy we need. So in this case, we calibrate the common envelope ejection efficiency. Maybe you can check our paper. The first author that GE. The first paper.
Perhaps you can give me the reference in the chat, or why?
Yeah.
GE 2020?
24 maybe.
24. Okay, thank you. I'll check it.
Yeah, you can check it. Yeah.
Thank you.
Thanks, Paul. So, I mean, in a way, it's actually interesting because I would imagine that within the implementation of binaries in population, it's the common envelope evolution is one of the big unknowns, right? You have the alpha CE, which reminds me a bit of mixing length theory in convection. You have this parameter that automatically says, well, you have this. So in a way, would you expect in the future models to go beyond this implementation of this simple phenomenological parameter, the alpha CE? Is there any way to improve on that one?
That would be too difficult. I mean, that's a challenge because actually Paul just asked a question about the common envelope, and also in good paper we compared the hot subtotal boundaries. We compared with our model, so we calculated the common envelope ejection efficiency. But for that, we found that the common envelope ejection efficiency is not a constant. Normally, we assume that's a constant, a parameter, a fixed parameter. But actually, we found it changed with the method ratio. So that makes things more challenging. So I think we need to do more work on that.
And one thing I found very interesting and very intriguing, you were saying that when you take into account binaries in old population, then you end up getting a mass to light ratio, stellar mass to light ratio that is higher than what you would expect in singles. So I don't know what your opinion is of all this business that has been, like, we already for over about 10 years or so, there has been this case towards a bottom-heavy IMF in the centers of the most massive galaxies. So when you look at the spectral energy distributions, you look at the dynamics, you find that on average you tend to have many more low mass stars, which translates in a way into a higher mass to light ratio. So, I mean, could you consider the possibility that this effect might be, rather than the IMF, could actually be that binaries in the dense regions in the center of massive galaxies, then the binarity will be higher. So in principle, that mass to light ratio will increase.
No, I agree. You raised a very, very good question. I have not thought before. Maybe we should check. Maybe because for massive stars, there are much more binaries. So if we take that, in fact, maybe we can change the IMF a little bit, maybe.
That's a possibility.
Thank you very much.
Yeah, because some of the, I mean, you know that some of the studies, so some of them are based on line strengths, but some of them are based on dynamics. They simply basically do Jeans modeling or any other methods or short cell modeling. Yeah. And what they end up getting is, in overall, the mass to light ratio should be higher than you expect in Krupa or in Chabrier or in Salpeter. So maybe the binaries will play a role. So that would be interesting to see.
Yeah. I think maybe it may play a role, but how big the role is that's the question. We should.
So looking forward to your paper in the future then.
Okay, thank you. Thank you very much.
Are there any other questions? Please raise your hand if you have questions. Okay, if not, yeah, I think, well, that was very, very nice. I really enjoyed a lot this talk. I hope all the audience has done as well. It's very interesting. So, Zhanwen, it's an absolute pleasure, and thanks so much for your talk. We will post this in the YouTube channel. So, all the very best.
Okay, thank you very much. Yeah.
Bye, everybody.
Bye.